Good morning, everyone. Thank you, Danny, for the opportunity to kind of be part of this tutorial week. So I have two lectures. One is today and tomorrow at the same time. So the instructions that I got from Christian was don't try to keep it as general as possible. So, and also the audience is going to be varied. So what I tried to do was not assume any background. I know that there are experts in DFT and practitioners of DFT in the audience. So this lecture may be a bit very introductory, for these audience. But my hope is those who have never been exposed to any electronic structure or DFT can go from high school physics or undergrad physics all the way to DFT in these two lectures, so that the first week of workshops have many DFT code discussions as well as method development discussions, and then you would have understood the basic background to be able to appreciate those talks. So what I'm going to do today is start from classical mechanics, introduce quantum mechanics, then introduce the many-body quantum problem, and then talk a little bit about how chemists approach this problem, and then I will introduce density functional theory, which was introduced in the mid-1960s, and how that all came about. So let me start off by, so let's say that we have a condensed matter system. So let's say we have, okay, maybe I shouldn't be using this side of the board to begin with. So let's say that we have a bunch of nuclei, and Zi is the atomic number of each of the nucleus, and let's say that the position and the momentum of each of this nuclei is given by P capital I, comma R capital I, and let's say that we have a bunch of electrons in the system, and the position and the momentum of these things are given by P little I, and I'm introducing a composite variable over here, xi, which gives both the position as well as the spin of each of the electrons. Okay, so once we have this condensed matter system, if I were to write down what the classical Hamiltonian for the system is going to be, is it legible for those at the back? Okay, great. So we have the kinetic energy of electrons to begin with. So kinetic energy of electrons is pi square over 2me. So we have a sum over all the electrons. We have the kinetic energy of the nuclei, which is and then we have the potential energy, which has three contributions. One is the electron interactions, which are given by summation over I, j, I not equal to j, and we have that, and then we have the electron nuclear interactions, which is going to be summation over I, summation over capital I, Ze square, so there's going to be a negative sign, capital Ri, and then finally we have the nuclear interactions, which are going to be given by and then we have I not equal to J, right? So that's the classical Hamiltonian. It's going to be the sum of the kinetic energy of electrons, nuclei, and sum of all these potential energy interactions. So once we make a transition from, of course, if we were to try to solve the dynamics of these equations, like we would construct the Hamiltonian equations and then solve them. Did I make a mistake?
Correctly, there's an E squared or not E squared?
Yeah, there should be an E squared here, yes.
And then, why do you have halves?
Sorry?
Why do you have halves?
That is because you don't want to. So here I'm not assuming that I is not equal. So I'm assuming that I runs from 1 through n and j also runs from 1 through n, and just that I is not equal to j. So if I write I greater than j, then I would not have the half. But if
you want so you don't want each interaction counted twice, but yes, it should be counted twice, right? Because it's one electron acting on the other, or vice versa.
But in terms of the energy of the system, it's just pairwise interactions.
I was good to flunk out of physics.
Yeah, so there's going to be a half. So because if you have 2 electrons, it's going to be just the Coulomb interaction between the pair of these 2 electrons, and it's going to be sum over all the pairs. Yes.
Question for the position xi, you have dotted. Is that NISI?
Yeah. So this is the
What kind of stuff?
so this is the position of the electron, and this is the spin of the electron.
So they are both in
So this is an R, right? It's not an N.
Yeah, this is the lowercase
So
r.
funny way of writing.
Yeah. So sorry. So this is my r.
Oh, just
It's not an n. It's an r. I'll try to be. So you can see that it's r. Sorry about that.
just R.
Yeah.
And also, it's a 3-dimension vector, right?
Yes, it's in 3 dimensions. Yeah.
And SI also 3-dimension vector.
No, SI is spin, so it's going to be spin up or spin down. So it's going to be a binary. Yeah. So it's going to be binary. It's either going to be, you can represent it 0, 0, 1, or minus half, half. Yeah. Okay. So that's your kinetic, or rather the total energy for the classical Hamiltonian. But now once you move to the quantum picture, so what you would do is you would start with the classical Hamiltonian, and then you would start replacing each of these variables with operators. And so the momentum operator for the electrons, or the momentum of each of the electrons, gets replaced by a momentum operator, pi, okay? And the momentum of the nucleus gets replaced by a momentum operator, p capital I, okay? And each of the positions also get replaced by the position operators. Now we can express these operators in any basis that we would want to. And typically you express these things in a position basis. So when you express this operator in the position basis, so this becomes IH cross times a gradient operator. Okay, and so this would be for the ith electron. So this would be IH cross that. And this, so when you express the position operator in the position basis, it would just return the position of each of those electrons or the nuclei. So that becomes Ri, and this becomes capital Ri. Okay. So now once, so that's how the operators transform, going from classical mechanics to quantum mechanics, and we are now expressing these things in the position basis. Now, if I were to look at the kinetic energy of electrons in the position basis, that is given by minus h cross square by 2 times me of del I dot del I, which is minus h cross square by 2me Laplacian corresponding to the ith electron. Okay? So similarly, you can have the kinetic energy of nuclei, and that will become minus h cross squared by 2 times capital Mi Laplacian square. Okay? And finally, like when we have these terms, those expressed in the position basis will remain what they are, because you replace each of the position in the classical Hamiltonian with the position operator, but when you express it again back in the position basis, these are the expressions that you eventually end up with. Okay? So I won't write them down again, but because these are the two things like, which change. And also in quantum mechanics, it is useful to use what are called as atomic units. So these are different units. So in the atomic units, you consider h cross to be 1, the mass of the electron to be 1. Okay, by the way, I forgot, because I always think in terms of quantum mechanics, I forgot the 4 pi epsilon naughts. So there will be a 4 pi epsilon naught in all these places. And you also have 4 pi epsilon naught to be equal to 1. And also the charge of the electron is 1. Okay? So in these atomic units, the energy is given by a unit called Hartree, because this is what like you will probably hear when you hear DFT talks in the first workshop. And 1 Hartree is 27.2 eV to the first decimal. And the length unit is going to be Bohr, and that's 0.528 something angstrom. Okay. So now once we have set this thing up, the governing equations in quantum mechanics are given by the Schrodinger equation. And when we are looking at ground state properties, that would reduce to what is called as a time-independent Schrodinger equation. And the time-independent Schrodinger equation is given by okay, maybe I want to bring this. Okay, so the time-independent Schrodinger equation is given by h psi equals E psi. And that's written in an abstract manner. H is the Hamiltonian operator, and psi is any abstract vector. So let me just put it this way. Okay, so now you can express this abstract eigenvalue problem again in the position basis. When you write this in the position basis, what you end up getting is, so the h is going to be given by these two, along with this, and the third term, like, which is behind. So, and I will use atomic units now. So I'll drop the mass of the electron, the 4 pi epsilon naughts, and then the E square. And what we end up getting is minus half Laplacian square plus minus 2 over mi. Okay, I need sums over here. Sum over I minus half Laplacian square sum over capital I minus half plus sum over I comma j, I not equal to j, and I have a half here, 1 over mod Ri minus Rj plus sum over I, sum over capital I, Zi by mod Ri minus capital Ri plus, so this is going to be negative because it's an interaction between a positively charged nucleus and a negatively charged electron. Or typically it's considered the other way in whenever you're talking about DFT and quantum mechanical calculations. It's the electron charge and the electron density which is considered positive, and then the nuclei are actually considered negative. It's equivalent, okay? So, and then finally we have Zi. There's going to be a sum here. Sum over I comma j, half I not equal to j, Zi Zj over mod Ri minus Rj. So this whole thing is my Hamiltonian, and then we have an eigenvalue problem here. So I'll also write my psi in terms of the position basis. So psi in terms of the position basis will depend on the positions and the spins of all the n electrons, as well as the positions of all the nuclei. Right? Yes.
I have a theoretic question, but only because I teach this, but but if you start DFT and everything else, materials, with a non-relativistic Schrödinger equation, then you end up with a lot of issues that are completely hidden from most people in the field, even practitioners.
Yes. So I should.
Yeah. Two things, right? One is the kinetic energy, right?
Mm-hmm.
Nobody in this field uses the non-relativistic operator, right? Everybody
Yes.
uses the scalar relativistic operator, at least by way of the pseudo-potential or whatever they choose.
Yeah.
But it's not taught.
Yeah.
And the other thing is that the spin sort of drops from the sky, but if you use at least the Pauli equation, then the spin would not be a problem at all, right? The spin would just exist as a natural property of the wave function.
Yeah. So all the points that Volker are making are really important. I should have mentioned this like right up front. Like so.
Less a request for you to mention it, right?
Yes.
The real question is,
Yes.
how should we be teaching this? Because I also don't have a good answer. I
Yeah.
go to the Dirac equation and say, look, this is how it comes from the Dirac equation.
Yeah.
But the fact that most textbooks just don't do this, right?
Exactly. So that's where I was kind of going to answer that. It would be ideal to really start. I mean, just like how I'm presenting this, starting from quantum mechanics and going to DFT and then talk about all the approximations. I think what would be nice would be to really start with the scalar relativistic treatment and then say that okay, when the velocities of your electrons are much less than c, then this essentially reduces to this form. So I'm with you on that. Just that I think pedantically many of the textbooks don't do this, and I think it would be nice to start with that starting point. And as Volker is saying, a lot of people in material science don't consider the effects of relativistic effects. I mean, it's the people who are in the really worrying about electronic structure calculations, its accuracy, and then what it means to sensitive properties, spectroscopic properties. Those are the people who really consider these things, but they can be important. At this point, we do so many DFT calculations in a high throughput manner. If you're doing a pseudopotential calculation, it may still be okay because some aspects of these relativistic effects have been incorporated into the pseudopotential. But if you're not, and you're doing an all-electron calculation, then you can be in real, you can have large errors when you're going to at atomic numbers which are high in the periodic table. So, yeah. So I don't have a good answer for this, Volker, but I think it'll be, from my personal perspective, I think it'll be nice to start from the relativistic picture, but I have not even prepared my notes that way. So, so I'll have to stick to this, yeah.
Are you actually teaching undergrads or graduate students in material science DFT and start relativistically? That sounds insane. Because they don't have relativity in physics. Now smacking them over the head when they not even know what a wave function is sounds like a pretty harsh step. Instead of telling them later, when the electrons zip fast around the nucleus, here's what's happening. Plus, we don't have a many-body version of relativity for the electrons anyway.
I think that some quantum chemists would disagree, right? They have a many-body version.
But this is approximate, it's an expansion.
Yeah, but if you start Dirac-Colchamp, for example,
Yeah.
you can actually write down the Dirac Hamiltonian and say, look, this is actually the structure.
But the Dirac is a single particle Hamiltonian.
Yeah, but it becomes...
And the whole point, what he's trying to do is introduce correlations. The Dirac doesn't have correlations in it. An exchange. Right? So I think the important point he's trying to get to is how we exchange correlation at some point.
Yeah.
That is very hard to do in a relativistic description because you start immediately doing your
you have to start from QED if you want to do what...
Yeah, well, and that's definitely not what you want to do to a material science student. Or physics student for that matter. I'm just curious if you do that.
It actually works to try and tell the story behind this, right? Which is that Schrödinger actually, so I don't know if people know this, right? But Schrödinger's notebooks exist, and I think they're actually online, but I saw a note version sometime ago. And so Schrödinger was not looking for this equation, right? Do people know this? I don't know.
No, I don't know.
So Schrödinger, I think if I remember correctly, Schrödinger spent about 6 months trying to find a relativistically correct action that would give him a wave equation, right? And so he found the Klein-Gordon equation, which is spin zero. So apparently, so this is, unfortunately I saw this many years ago, right? But he goes through these notes and tries action after action, and eventually he came up with this action here, which gave him the non-relativistic version. But he knew that this was not what he was looking for. Right? So even Schrödinger at the beginning knew that he had actually found the wrong equation. It's manifestly not relativistic, right? It cannot be relativistic. But he didn't know how to do it right, and so he published this one, and that's good. Worked for him, right? But if you started from there, then you can actually at least motivate why you should go to a different equation, because this one isn't the one. That, to an extent, solves the problem that we end up training believers in the non-relativistic version of Schrödinger's equation. So if you have an electronic structure code and you try to explain to people that differences arise because of different treatments of relativity, they're usually completely surprised, right? Or many of them are surprised.
That's right. But I think the better strategy for teaching is to start with this first, teach them, and maybe mention every night. We're going to later talk on that there's additional terms, then they're not too surprised, but that you don't lose them right here. I think if you start about relativity at that stage, you're done. They will walk out of the room and have learned nothing. At least my students usually overwhelm them. Right? There's a lot of stuff understanding
maybe we should have this conversation during the coffee. So we have the time-independent Schrödinger equation over here, which is an eigenvalue problem. So we have now written this in the position basis. Now, one of the important aspects over here is that the wave function is one of the key quantities that we are after, and which has all the information about material properties that you want to compute, because that's computed as an so this is considered to be the state vector, and once you have this, the expectation values and the standard deviations and other things of any observable can be computed using this wave function. So this wave function is a multidimensional function, so it depends on the positions and spins of all the n electrons, as well as the positions of the m nuclei. Now, it's common in electron structure calculations to do what is called as the von Oppenheimer approximation. I think it's EI. And what this says is that, well, okay, I'm missing an MA here, so there should be an MI, so MI over here. So what the von Oppenheimer approximation says is that the mass of each of the nuclei in the atomic units, where the mass of an electron is 1, is much, much greater than 1, right? It's the order of 10 cubed. So what you can do is, because the kinetic energy of the nuclei is going to be very small compared to the kinetic energy of the electrons, you can neglect this operator. You can neglect this operator, as well as you can think of the dependence of the wave functions on the positions of the nuclei, not explicitly, but as a from a parametric standpoint. That is, you have a given positions of the nuclei, and then your electrons are zipping around like much faster. So you solve these equations for a fixed positions of the nuclei, and that's what the Born-Oppenheimer approximation gives you. Okay, but if we still, so then the wave function is still dependent on the positions and then the spins of the n electrons, right? And that, if we see, lives in a 3n dimensional space. So that's the curse of dimensionality over here. So if you take even a nitrogen molecule which has 14 electrons, and you discretize the whole real line just by 10 points, a very coarse discretization, then we're talking about an eigenvalue problem whose each dimension, or the size of the matrix, is going to be 10 to the power 42 by 10 to the power 42. So it's not practical to be able to do any calculations using full quantum mechanics. So this is where...
What's the second term in that expression?
Oh, this is for the spin.
That's for the spin?
Yeah. So sorry? Yes, I should say.
It's really functions in that space, right? Not-
So
Okay, better. Okay.
yeah.
It's really functions in that space.
Yeah. So this is on functions of that space. So I'm really saying that this is an n-dimensional function. Yes. Yeah. So So and the curse of dimensionality was known to people for a very long time. So in starting from the 1950s, people started asking the question, okay, how can we reduce the computational complexity of this? So one of the things that they started looking at was, well, this is a multidimensional function. All tensor structured approximations and low rank approximations are very popular these days, but these were the ideas that chemists actually explored, where they were looking at, can we go to a lower rank approximation of this multidimensional function and then end up with a more simpler formulation? So what they then did was, well, can I write this as simply a tensor product, right? So naively doing that is not going to be right, because this does not satisfy the antisymmetry of the wave functions people know from quantum mechanics. So the antisymmetry says that if you consider a multidimensional wave function and you take any two indices over here, because all these are identical particles, all the electrons are identical particles. So if you flip the positions of the electrons or the spins, like what you end up getting is a negative sign. So this wave function has to be antisymmetric. So here I'm flipping xi and xj, and you pick up a negative sign. So this approximation is not going to satisfy that antisymmetry. So what you can go and do is antisymmetrize this product, this one rank tensor product, and that is what gives you what is called as the Hartree-Fock approximation. So to satisfy this condition, and if you want to be in this one particle approximation, so what you are looking at is you are approximating this wave function using what is called as a Slater determinant. And that is given by 1 over square root of n factorial determinant of psi1 of x1, psi1 of x2, psi1 of xn, psi2 of x1, psi n of x1, Okay?
Can I ask a quick question?
Yes.
I thought that's only true when I exchange the position of electrons that have the same spin.
Yes. Yes.
We should actually write it as R's here. And you should actually have to write that out as two separate terms, one for the upspin electron, one for the downspin, because you have an upspin and downspin is later determined in the end, right?
No. I think even the spin exchange should pick up, right? So because this is going to be in terms of like both the position and the spin.
When I exchange two electrons which have opposite spin, nothing symmetrically happens.
Not in terms of
Pick up the
the
minus
wave
sign.
functions.
Jörg? Am I making that up or? When I have only when I have equal spins.
Yeah.
When I exchange them, I get a minus sign.
Yeah.
Okay. So this is just a little quick notation where we
Yeah.
right, but you have to be careful with the spins.
Yeah.
Okay.
So this is basically the yeah. So yeah. I think I should make a quick note that like I'm using the X, which is a composite notation, but this essentially happens like when you have a spin. This happens with exchange of the positions, but I have to go back and think. Yeah, because I do know that like the Slater determinant involves X's over here. So and I although we say X1 and X2 over here, X2 can be like really R1 and like a different spin. And once you flip these things, like you would pick up a negative sign. So
I mean, it's fine because the exclusion principle that underlies it says that you cannot have two things in the same spin. So if you exchange two variables,
It ends the same
in
position.
the same position, right?
Yeah.
What I'm just saying is that so therefore, if you insist on this with the spin taken into account,
this would become
there's no
zero.
contradiction because if you're exchanging two variables, they're very different values of xi. So your wave function is not zero. And the way you derive Pauli exclusion from this is to say that if xi equals xj, then we exchange xi equals with xj, and then we get the
zero.
same
That's
thing. We
right.
get zero.
So if the Pauli principle is still fine.
Exactly.
I get it.
So, and I think, but this
so the rest is still fine. You're saying
but
it
that
doesn't
should
affect
be
any of the other
equivalent-
stuff.
It should be equivalent to the Pauli principle, so therefore it should be just that.
So this fulfills the Pauli principle. I agree.
Yeah.
And
I'm
I'm-
just wondering
I'm
if
just
I
saying that that
exchange
should be-
two electrons which have opposite spins but the
Same position.
That's
do I pick up a minus sign in my wave function? I don't think I do.
I think we,
So phi
The notation I think is fine.
yeah.
Because x1, let's say if you have a spin up and a spin down,
And I
you would have a
exchange
different
them.
x.
exactly.
So I think that's the main point. So in this way, it's not the way we are writing it typically. But I think it's perfectly
I'm just wondering
fine.
if I exchange two electrons which have opposite spin, I exchange them. Does my wave function pick up a minus sign in that case? I didn't
Yeah,
think
so
so.
this-
You can make
That
it,
says
you
yes.
can choose it so that it's
You can
true.
choose it.
Yeah.
So it doesn't hurt anything.
Yeah.
So isn't actually, so I'm sorry, I missed the question, but don't you just actually define different Slater determinants for the different spin channels?
That's what I'm talking about.
Yeah, so
the end of the
this one is kind of very generic. Like I'm not looking at the restricted or unrestricted Hartree-Fock. So
The X shouldn't be an X. I think the X should be an R, and the order should get an arrow at the bottom, and it's either spin up or it's spin
yeah,
down.
so you can write this as a
That's exactly
function
my
of
question.
R, and then a spin up and spin down.
But it's the same
I'm
mathematically?
saying that if this more complicated determinant can just be packaged into one bigger determinant like that.
Yeah.
This is like, because of the different spins, this is like a huge matrix with it allowing for the different spins.
When I write it all out, all the
I
product
imagine
terms, that I'm going to end up with essentially writing it out as two individual determinants works fine. Okay.
Fokker.
I have not seen that. Okay, because I usually
I just wanted to comment that this is another reason why I asked this question initially, right? Because you run into exactly this problem when you teach it.
Oh, yeah.
If spin drops from the sky in the non-relativistic version, then you run into exactly this problem.
you get very sloppy suddenly on the middle there. That's right.
Oh, yeah, sorry.
Okay, cool. So so this will be the form of the many-body wave function that satisfies the antisymmetric nature. And of course, one thing that I want to emphasize over here is that the inner product of psi I and psi j has to be equal to delta ij. So when I'm considering this, this would be the form taking into account that each of these things are orthonormal wave functions. Okay. So, and if you look at we do that because eventually that will translate to the normalization of this many body wave function as well. Okay, so now if we look at the energy, so this is one approximation. So now if we look at the energy of the system, and this I will call it as E Hartree-Fock. So this is the Hartree-Fock approximation. And so the energy in the Hartree-Fock approximation is essentially given by, so if I call this as psi Hartree-Fock, okay, so the energy is going to be given by the expectation value of the Hamiltonian, assuming that you have a single Slater determinant over here. Okay. So now if we want to compute what the energy is going to be, we don't know what these wave functions are. So I have to minimize this particular energy with respect to the choice of the single electron Hartree-Fock orbitals that I end up getting. So once we do that, so if I may erase this. Okay, so if you minimize over all the single electron wave functions of psi Hartree-Fock of h hat psi Hartree-Fock, okay, so that is you write the Euler-Lagrange equations corresponding to these. That minimization, you end up getting the Hartree-Fock equations. But before maybe I'll write down like first what this energy is going to look like. So if we look at E Hartree-Fock, that can be decomposed into the following terms. So you have your HI to be so the external potential is nothing but the potential provided by the nuclei, so it's going to be just the Coulomb potential. And your Jij, which is called the Coulomb integrals, are given by, it's going to be a double integral, psi I of x1, psi I conjugate of x1, mod r1 minus r2, psi j conjugate of x2, psi j of x2, dx1, dx2, where I'm integrating over both the positions and the spins over here. So this is called the Coulomb integral. And finally, we have what are called as the exchange integrals, which is Kij, and that's psi I. And this is what is called as the exchange integral. Okay? Yeah.
Still back on the previous. So, CIs are, this C Hartree-Fock is supposed to be a wave function, right? So
yes.
It should have square integral 1.
Yeah, and
Which you would get from orthonormality of the PCIs if you don't put the 1 over square root of n factorial. Right? Because you get this determinant times itself, which then by orthogonality is the determinant of what's inside times transpose, which is identity.
No, so eventually what you're interested in is the inner product of this multidimensional wave function with itself. So the number of terms that we end up getting here would be essentially many combinations multiplied by many other combinations.
Itself, right?
Sorry?
It's the determinant times itself that you have to integrate, but the determinant is multiplicative, so you just multiply the matrices.
Yes, but you get many terms out of taking the determinant over here.
Ah, I see, I understand.
And that is where you get your n factorial. Yeah.
And see here, you're still minimizing over
these, yeah, exactly. These essentially, yeah, I'll write it down. So you're minimizing this subject to the constraint that these have to be orthonormal. So that's what gives you again an eigenvalue problem, which looks as follows. So, so if you do minimization of, let me write it down again. So if we minimize psi1, psi2, so on up till psi n, for that energy, which is E Hartree-Fock, which I've written down explicitly in terms of these psi's, right? Subject to the psi I to be delta ij, then you end up getting the Hartree-Fock equations, which is again an eigenvalue problem. So you have an operator acting on some psi I, which is summation over j epsilon ij psi j. Okay. And the action of this operator on psi i's are given by these expressions. So let's say that, okay, so the Fock operator, so the F is called the Fock operator. So this one is called and the Fock operator is comprised of a Laplacian, the external potential, and then this other operator which comes from the Coulomb and the exchange integrals. And the G itself is given by a J minus K operator. And then the action of J acting on any particular function x1 is given by the following. So it's summation over k integral psi k star of x2 psi k of x2 1 over mod r1 minus r2 phi of x1 dx2. And the action of the k operator on a function is given by okay, so that's eventually what you end up getting. Yeah.
That's one more question.
Yeah.
Is it obvious that in your Coulomb integral, you have all zip size independent of spin contribute?
Yes.
In the exchange integral, it's only like spin electrons that contributed to the exchange integral, and the unlikes have to cancel in that form. Is that clear from that integral form that if x1 and x2 have opposing spins, that contribution is zero? I don't see that.
Yeah, so
that's the same as my question before.
So one comment that I want to make is JII will be equal to KII. So self interactions of the electron with itself are cancelled over here.
Yeah, that's right.
And your question is if like you have J to be, but
If
so,
I have x1 and x2 have opposite spins,
but that is
determine the integral is 0.
yeah.
How do I see that?
So the way you see that is that if you have two electrons occupying the same orbital, then your psi j is going to be written as the same phi as your psi I. This will have an alpha spin, this will have a beta spin.
But if they don't occupy the same orbital, if they're in different orbitals,
Then it
and
doesn't.
they have opposing spins,
Yeah, then
so
that
it should be 0.
no.
We don't have exchange interactions between opposite spins.
Uh,
Yeah.
Right?
But I think you
it
see
drop out?
yeah. But if you would, let's say, write the integral a bit different, or so that you have d r d sigma.
There's a
so for the
ds
spin,
here.
then you can easily see. So if you integrate, so then you have, let's say, your spin integral and your space integral.
Right, but I have a
And-
spin integral for 1 and a spin integral for 2. So I have the sum
Yeah.
of spins.
Yeah, but they are orthogonal
So I have
among
terms.
themselves. But they are orthogonal amongst themselves, right? So let's say that you have an alpha spin and a beta spin, which are not occupying, and they have nothing to do with like, this R1 and R2. So eventually what happens is this dx1, dx2 becomes ds1, ds2, and then they are,
But I have terms in there where the one is upspin, the other is downspin. It hasn't dropped out yet.
I think it would be much easier if I would write, let's say, the psi into psi r times chi for the spin, degree of freedom. And then you can also replace,
And
let's
then
say,
make
the
the integral
dx. And then you have just, let's say, the chi's for the spin. And then you take the integral over, it's the spin integral, and then you see immediately that the equal spins drop and become one.
In the
and
exchange
other-
integral, but not in the Coulomb integral.
In the Coulomb, it's the same. So then you can, but there you want, let's say, to have
On the
always.
Coulomb integral, they don't drop out, right? The Coulomb integral, I have Coulomb interaction with
Let's say, so,
opposite
but-
spins.
Or let's say, so that's a hard tree. And for the hard tree, you have, of course, only equal, let's say, so the same spins. So you want to have, let's say, the same size in there. And therefore, it becomes one. I think everything is perfectly fine if one writes it out. Because,
Is there missing conjugate in the KIG?
Yeah, sorry, the
yes,
second one is an asterisk.
yes, there is a
it's
missing
only
conjugate.
compact the notation.
Yes.
I think you
Let
could
me
much
make sure that I
easier
get
see
it
If you really
When you write it out-
if you write it out, so then.
Despite its effects, the integrals look very similar in both cases. In one case,
Yeah,
all the
so,
opposing spins and
let me
equal spins
see.
show up, and the other one, they all drop out.
Exactly.
Interesting, okay.
I think there should be a conjugate.
Yeah, the first one there.
Yeah.
So the difference between them two is just
The indexes like, yeah, exactly. The indexes like, get flipped. So if you have like, for instance, so here you have an I and I, and then this becomes an IJ. So it's, okay.
Works because, let's see, so in the, let's see, for the Hartree part, you have psi I times complex psi I conjugate. And therefore, the spin channels are so only, let's say, are automatically always the same, so it's becoming one, so you don't have really to worry about it. Or,
So I think
only the law, let's say, so for the exchange.
all of them will work out like,
IJ, there you really, let's say, the spins become important for the upper one, so they immediately cancel out. Because you have psi I
Okay,
times psi
I think I see it. Yeah, thank you. Thank you very
Yeah.
much.
Okay, so one remark I want to make is that eventually when you did this minimization problem, so these are the Lagrange multipliers that are appearing because of this constraint over here, and this is essentially an eigenvalue problem. You can also convert this into a canonical eigenvalue problem by just an orthonormal transformation where then this matrix epsilon ij becomes a diagonal matrix, and then you can see that as an eigenvalue problem there. But what you have is this is essentially a nonlinear eigenvalue problem, and that's what you will see in density functional theory too, where you have the solutions, which are the size, actually also appear in the operator over here, because the action of the operator on any function involves the size, right? So you have to solve this particular problem in a self-consistent manner. And one of the things that I want to emphasize with the Hartree-Fock approximation is there's some nice things about the Hartree-Fock approximation, which is that self-interaction error is not present. So what I mean by that is, as all this discussion is surrounding around that self-interaction error, an electron does not interact with itself, right? Which will not be the case once you go to the density functional theory picture. And some of the errors in DFT have been significantly attributed to this self-interaction error. But this particular exchange integral, the fact that this KII is the same as JII ensures that the self-interaction error, perfectly cancels in the Hartree-Fock picture. But what the Hartree-Fock approximation completely misses is the fact that this eventually came about as essentially a rank 1 approximation, right, via this single Slater determinant. So if you think about this particular thing as a tensor, from a tensor structure standpoint, and it's a low rank decomposition, you are obviously, from a variational standpoint, getting an energy over here which is higher compared to the true ground state energy. Now, the natural thing to do is not consider one Slater determinant, but consider many Slater determinants. So how can we get many Slater determinants? I'm not going to write this down, but I'm just going to speak as to what the main idea over here is. So let's say instead of just taking n functions, we take m functions where m is greater than n. Then we can get mcn such Slater determinants. And then the wave function that we eventually want to compute, the many-body wave function, can be expressed as a linear combination of this m choose n Slater determinants. Then we have two aspects to optimize on: all these m single orbital functions, as well as the coefficients that are coming in front of these m choose n Slater determinants. So if you do this formally, and there is a nice work by Gero Fresiche, it's a paper in Archives of Rational Mechanics, which I encourage, if you're interested, to look at it, that shows that as m tends to infinity, you recover the full quantum mechanical solution. But of course, that's a formal result. In practice, what one has to do is you have to be very smart about choosing what Slater determinants what you want to keep and what Slater determinants you don't want to keep, right? So typically what people do is they do a Hartree-Fock calculation. They compute not just this low-lying, which are states that are occupied, right? But you also compute virtual states, because once you have the Fock operator, its action, you can also compute the higher unoccupied states as well. Now that is used as the broader basis to construct these Slater determinants, and you're not optimizing on the wave functions anymore. You're only optimizing on the coefficients in front of the wave functions, and that reduces the cost, right? And also, but that's still a combinatorial problem. You still have an m choose n Slater determinants. Then what people do is they use what are called as single excitations. That is, they don't consider all the combinations, but they say, okay, one occupied orbital is jumping into one unoccupied orbital. So it's just the number of Slater determinants that they consider will reduce, right? So these are all the various tricks that chemists do to kind of reduce the computational complexity. This is what leads to multi-configuration equations, coupled cluster, type ideas that some of you may have heard of. So this is what the quantum chemists have pretty much pioneered over the past 5 decades to solve that particular many-body challenging problem that you have. But then in the mid-1960s, Hohenberg, Cohn, and Sham came up with something which is quite remarkable. So, and I think that pretty much changed the landscape of many calculations, especially in material science. And that is what is density functional theory that they proposed. Yeah.
Just more of a physical question. So
Yeah.
if you would stay in the single determinant Hartree-Fock, so what kind of physics effects? And what kind of things mess up?
Yeah, so relating to that point, one important note that I have to make before I go to DFT is, as I mentioned, the energy of this is going to be higher than the true ground state energy, just from a variational standpoint, because I've chosen a restrictive form of this many-body wave function, right? So now, if you look at the energy difference between the true ground state energy and then the Hartree-Fock energy, this is what is called as the correlation energy, which is what Hartree-Fock completely misses. And this is basically the correlations of the many electrons that are interacting with each other, right? So here you have reduced this, like, primarily to single. So even if you think about the Hartree-Fock approximation, this is reduced into a single particle picture. So you have n electrons, which are, once you solve it self-consistently, you have n electrons, and they're moving in some kind of a mean field. So you've converted a problem from a many-body picture to a single particle picture, where all the interactions that are missing are essentially these so-called correlations, right? So you miss the correlation as to if a particular electron is at a given point, how it influences the other electrons, not just from a mean field perspective, but beyond a mean field perspective. So that's the physics that it completely misses. And this difference, which is the correlation energy, it's very small. It's typically of the order of like 1% of the total energy. But that is what is most important to binding and many material properties. That is also the reason you need to get the DFT calculations very, very accurate, because not just in terms of the theory, but also in terms of the discretization, because you're talking about the total energy system is going to be large, but it is these small differences in energies which essentially control all aspects of chemical as well as material properties. Did I answer your question, Danny? Other questions? Yes.
I'm just maybe a bit of a naive question on the derivation. For me, there's a bit of a disconnect when we have this minimization in the preceding equations. I'm just curious, at what point does this minimization actually occur?
So this is basically the restrictive form of the wave function that we're taking, right? And if I plug in this particular form in terms of these single orbital wave functions or single electron orbitals, this gives us the energy can be written in terms of this psi1 through psi n's as follows. Now we end up doing a minimization over these functions, which are not determined, subject to the constraint that these have to be orthonormal. And that is what give you the Fock equations. I think erased the board, like, which is right here. But that's what give you the Fock equations, right? Which is just Euler-Lagrange equations.
If you do not constrain C to be of that form, then you get the true lowest eigenvalue of
Well, not really. So we have already
saying if you just take any wave functions.
Exactly. So if you consider like a multi-dimensional wave function, right, which is high dimensional in the 3n dimensional space, and do this variational problem, that's what gives you the true ground state energy, E0. Now, because we have chosen a restrictive form, which is more like a rank 1 approximation for this many-body wave function, you end up getting an energy which is higher compared to the ground state energy. So that error is what is typically called as a correlation. And whenever you're going to hear about DFT talks, you're going to hear about correlation, right? And so-called exchange correlation. I'll also talk about what the exchange correlation is in density function theory.
Just to follow up to Danny, so you mentioned the difference between the Hartree talks and the rest of the whole energy, but do you have any intuition as to why Hartree-Fock has tendencies for energy differences? So things like binding energies, band gaps, like, we always tend to say, well, Hartree-Fock's going to overestimate gaps.
Yeah, so what happens is that what people have observed numerically, and Virginia, maybe you have better answer to this question, even from an applied math standpoint, so please add to it. What people actually see is that when you do Hartree-Fock approximation, you get an over-localized orbitals compared to like what the true many-body wave function is. So let's say we do the Hartree-Fock approximation, we compute what this many-body wave function is, and see how localized like this many-body wave function is. That turns out to be much more localized than what it has to be compared to the true many-body wave function. And that is what like causes kind of an overestimation in terms of energies. But when it comes to differences, like, I mean, that's what comes as overestimation of like band gaps and like, homolumal gaps and other things. But when it comes to other aspects like where...
Well, why is that? I mean, first of all, I get the fact that it's over-localized, but I don't see where it comes from.
So once you over-localize it, what happens is the kinetic energy operator becomes like more, the contribution in the kinetic energy operator becomes more, as well as the Coulomb interactions become higher because things are much more compact. And it essentially is not looking at the fact that the presence of an electron at a given point is actually going to push out my wave function a bit further out because essentially that's basically what is missing in Hartree-Fock in terms of like what it sees. Did I answer your question?
Maybe it's better.
Okay. Yeah.
Just let's say physical interpretation, so which I like, so why Hartree-Fock is really giving a too large band gap. So the issue is that if I have, let's say, an electron in the valence band, this is seen by Hartree-Fock. And like you are saying, so it's really fully free of self-interaction. If I go into the conduction band, this electron is essentially not present at all for the electronic system.
Mm-hmm.
And that means so it's not screened.
Mm-hmm.
So in this way, if I screen my electron, of course the energy goes down. If I have no screening at all, so it stays way higher. And that's essentially the explanation. So why Hartree-Fock is giving pretty good valence band states, because there's a full screening and everything is in there, but empty states are completely absent.
Yeah.
And that's really the success then, or what DFT is doing much better. It's overdoing it, of course.
Yeah.
That's for me, obviously, let's say, the physical explanation. So why, let's say, the band gap in Hartree-Fock is so much higher.
Yeah, and just to follow up on that line of thought, so people look at like this exchange correlation hole, which is kind of what is the probability that an electron like wants to be at a given point? Like, is it preferable? It's not preferable. So because the correlations are completely missing. So the exchange correlation hole, I mean, when you're in the Hartree-Fock, you only have the exchange hole. You don't have the correlation hole at all. So that essentially goes back to what Jörg is telling, that it doesn't see. So because the true many-body picture, if we want to even think about it this way, is actually the multi-configuration equations. That is, the single particle wave functions can access these higher states as well, and then you do an optimization over the coefficients in front of those. And those bring about like a probability of an electron, whether it wants to be in a particular state or not, that is described by the exchange correlation hole. And missing the correlations are what like give you higher energies. Yes.
I think this really gives us a nice picture of what correlation is, so Richard, what you were asking. So essentially, if I put now my excited state in the Slater determinants, so in order to get, let's say, the next one, so this is really a new configuration. So now I have a real electron, and this is screened then by all the surrounding electrons, and therefore I get a better description. So we get then really a direct physical explanation what correlation is about. So essentially really putting, let's say, realizing different configurations so that electrons can, let's say, go into, let's say, single electron can go in there, I can have two electrons in the conduction band. So this are all, let's say, the approximations that quantum chemists are doing in order to get then a better description.
Yeah. Okay, so now let me go to density functional theory, which the main statement of density functional theory is that, so the ground state properties are solely a functional of the quantity called electron density, which is the probability density of finding any electron at a given position R. And the real success of density functional theory has been that you've now reduced a problem from solving for a many-body wave function to solving for a problem which is in a three-dimensional space, right? So that's what dramatically reduced the computational complexity. Yeah.
You done?
Richard, yeah.
Just one comment, and maybe you get to that. In that statement, it's often stated that way, but the real statement, Hohenberg and Kuhn made, that all properties of a solid are functional of the ground state electron density.
Yes.
The ground state needs to be in front of electron density because also all the excited state properties are functional of the ground state density.
that's the
any property, because it's when you look at the proof for the Hohenberg cone theorem, once you know the ground state density, you know where the atoms are. Once you know where the atoms are, you know your Hamiltonian, you're done, right? It's that simple of a proof. And so in other words, every single, and there is actually some recent developments which have looked at excited state functionals, which try to calculate what is a functional for an excited state, knowing only the ground state density. It doesn't work the other way around. Knowing the excited state density gives you nothing about any of the properties. Right? And that's a very important distinction.
Yeah, it is a ground state. Yeah, it is a ground state density. I mean, and that's why ground state properties is a function of ground. Yeah, so this should be ground state electron density.
And all properties. Once we actually do practical density functions here, of course, we only look at ground state properties. But that's for other reasons. That's because we're not smart enough to write on the exchange correlation functional completely.
Yeah. Thank you. Other questions or comments? Okay, so the proof of this is not too difficult. I'm not going to do it the way Cohn and Sham did in their original paper. I will use what is called as the Levy constraint formalism, because it's, I think, more intuitive. So we know that the ground state density is essentially you minimize over all admissible so these are many electron, many body wave functions, and the constraints, of course, that this has to be antisymmetric, and this integrates to n electrons, let's say, right? Because it's an n electron system. But I think before I do this, I think I want to first just write down what the expression for what the electron density is in terms of the many body wave function, because that's going to be important. So the electron density, so let's say rho of R1 is n times you do the integration of mod psi. So this is the many body wave function. So take the mod psi square of this, and you integrate over all the n-1 positions as well as the spins, and only the spin of one of the electrons, right? So if you integrate over all of them, you basically get, it's a normalization, right? And which is essentially saying that integral of rho should be equal to n, right? So which is, you integrate all the electron density rho, you end up getting the number of electrons in the system. So this is your electron density. Okay? So now the ground state density is given by psi h psi, right? So not assuming anything about psi over here. This is the many body wave function. And now h has, so I'll denote the kinetic energy electrons by T. And then we have the electron-electron interactions, which is that. And then we have the electron-nuclear interactions. And then we have the nuclear-nuclear interactions, right? So these are all the various operators that we have in our Hamiltonian over here. Okay? So now, then I can write E0 as minimizing over all admissible wave function psi of psi t hat plus VEE plus VEN plus, I'll write EZZ, because as I told you in the Born-Oppenheimer approximation, the wave function is not explicitly dependent on the positions of the nuclei. So you can pull this operator out, and then that energy, which is the energy of the nuclei interacting with each other, is essentially classical. It's treated in a classical manner. And this one is the electronic part of your energy. Okay? So now if I were to look at this, the kinetic energy is sum of Laplacian operators, each Laplacian operator corresponding to every electron. And the electron-electron interactions depend on the positions of two electrons. So this is a non-local operator, and this is a two-electron operator. Whereas if we look at the electron-nuclear interactions, this is an operator which depends at a time only on the position of a single electron, right? You can see that it only depends on the position of one single electron. So if I were to like just take just one term, which is or let me say R1, because this is a function of like only one electron, and this has this kind of an integration, this reduces to, and I have like also sum over, sum over I. So this reduces to essentially integral of the electron density R1 times sum over I Zi by mod R1 minus Ri. Right? And then there's going to be a 1 over n because there's an n factor there. And that's going to be dr1. Okay? And also, like we have a sum over little I over here, right? But you can see that plugging in any other Ri is only going to change this variable from R1 to Ri. And that's a dummy index anyway, right? So I pretty much like, get the same terms which are multiplied n times, and that cancels with the 1 over n over here. And then what you end up getting is eventually the psi v E n psi is equal to integral of rho of r times the external potential dr. Okay. So what happened over here is when I took the inner product, this term is only dependent on the electron density. It is not explicitly dependent on the many-body wave function. But these first two terms are actually dependent explicitly on the many-body wave function. Okay? So then what you can do is you can then go to this minimization problem, which is minimize over all psi of psi h psi, and then write this as okay. And now the minimization over psi can be split into two minimization problems. So have the minimization over psi, these first two terms like actually still depend explicitly on the many-body wave function. So you can write this minimization over as two minimizations. One, a minimization over rho, and another, a minimization over all psi which are giving me a given electron density rho. Right? So these two combined together will become a minimization over psi. And then what you have here is, let me put it this way, and then you have psi d hat plus integral rho times v external plus e zz. Okay? Now the key there was really this one electron operator, which ended up giving us this term, and that's why the key quantity of interest is the electron density. Now if we look at this inner term, which is you're looking at minimizations over all many-body wave function psi, which give you a particular electron density rho in the function space. Okay? Now, if you're looking at that, this has no information about what material system you're talking about. Because all information about the material system you're talking about is in this external potential, which is the Coulomb potential that's given by the nuclei. So this term, which is inside of the bracket, so if you were to do this thought process, Pick a particular electron density rho, do this minimization, you get an energy. Do this for the whole function space, admissible function space. And there are again theorems like, which say that the admissible function space has to be where square root of electron density has to be in H1. So do that for all of them. This gives you a functional of rho, right? Now, this is a universal functional, which is called as the Hohenberg-Kohn functional, which solely depends on properties of electrons, nothing about the material system. So we know that there exists a functional, we just don't know what its representation is, and that is where density functional theory as a theory is exact, but approximations come in because we don't know what the true functional form is. Now, what Kohn and Sham did in 1965 is to, take this functional, and they did a very clever split. So they said, let's take f of rho, and then write this as what is called as Ts of rho, and then Eh of rho, and then all the unknown terms are split into, are lumped into this other energy called the exchange correlation energy. Now, the picture that Kohn and Sham were looking at was, well, there exists this universal functional. We don't know what that is. But now let's think about, you have a many body picture. Let's think about an equivalent non-interacting picture. So the many body picture is an interacting system of electrons. But let's replace that with an equivalent non-interacting system of electrons, which gives the same electron density and the same energy as that of the many body picture. Okay? So because this is a mean field idea, Kohn-Sham DFT is a mean field idea, and because the electrons are not directly interacting with each other, but they're moving in the mean field of other electrons, there are no interactions between the electrons themselves. So this Ts of rho is essentially like if you were computing your n Kohn-Sham orbitals, that would be the expectation value of the kinetic energy operator corresponding to the Slater determinant of the Kohn-Sham orbitals. Okay? So now that will be known if we compute the psi i's. EH is the classical electrostatic interaction energy. So EH is called the Hartree energy, which is nothing but rho of r prime, rho of r, mod r minus r prime, dr prime. This is a classical electrostatic interaction energy. We know what its form is. And all the unknown terms are now lumped into this functional, which is called the exchange correlation functional. So why, they did this particular split the way they did because once we take the Euler-Lagrange equations of this variational problem, which is minimizing over rho over here, once we take the Euler-Lagrange equations, you end up with something similar to the Hartree-Fock equations. But now there's a mean field that's not just coming from the exchange contributions, but there's also a correlation contribution. Of course, you don't know what this is, and this is where all the modeling in Kohn-Sham DFT comes in. Right? So it has a similar structure of the Hartree-Fock approximation, but now with a correlation which can possibly be modeled. And so that's, I'm just going to write down what eventually the equations look like. So once you do the has to be equal to, it's not going to be equal to 0, so plus something else equal to 0 because you have also a constraint on the total number of electrons. Yeah. So eventually, once you take the variational formulation, what you end up getting is what are called as the Kohn-Sham equations. And the cone-sham equations are given by your minus Laplacian plus VH plus V external. Okay, let me explicitly write it out. VH, which is a function of rho, plus V external, which is a function of the positions of the nuclei, plus Vxc, which is a functional of rho, times psi I equals epsilon I psi I. Okay? Yeah. So that's why I said like there's some more terms which comes from the constraints. No, the exchange correlation potential will just be the functional derivative of the exchange correlation energy. Yeah. So I'm essentially talking about just the cone-sham formalism, not the generalized version of the cone-sham formalism where you have the exchange explicitly come out. No, I'm just doing the first level.
And you also, so I'm wondering, this is just because it's a constant in the field. So the representability question here is much more difficult than in Hohenberg-Kohn, right? So in Hohenberg-Kohn, representability I think is more or less fine, but in cone-sham it's not, I think. So it's not clear that you can always find a single particle density that is equal to the many electron density.
But according to this particular split, it should be, right?
No, I think there are counterexamples. At least there used to be, unless they're debunked in the meantime in the early 2000s or so. So for symmetric.
Yeah. So what Volker is mentioning is that from the proof that I've shown, it's clear that f has to be a functional of rho, clearly. But now once I split this as Ts, EH, and EXC, the Ts is a functional of rho, but it's indirectly a functional of rho.
Yeah, we can only do that if a single particle system actually exists that has.
Yes, but that comes down to the question of V representability, right? So if the electron density is whether it's V representable or not, and if we have a V representability, then we have something which is an exchange correlation functional. Yeah, this is N representability. Yes. So what essentially Volker is coming to is that this is a functional of rho, but eventually this is computed in terms of the single electron cone-sham orbitals. I know that the sum of all these things has to be solely a functional of rho. So from that, there is no guarantee that this will be solely a functional of rho. It can also be a function of the wave functions. But if you go to the original Hohenberg-Kohn theorem, what it says is that there's a one-to-one map between the electron density and the many-body wave functions. That is where the electron densities that you're really talking about are those that are coming from a solution to a true quantum mechanical problem. So those electron densities are what are called as V representable. And also one of the mathematically open questions is that we know what is the function space of electron densities for N representability, which is square root of rho has to be in H1, but we don't know what is the space of V representable densities. But as long as the electron density that you're going to get is going to be a V representable density, then this exchange correlation functional will solely be a functional of the electron density. So I need to make that remark. Did that address your comment, Volker?
Yeah. So the reason I'm asking is because I'm wondering if this aspect is actually finished, right? So so at this point, DFT has become such a black box method that there is a large community that thinks that PBE is enough, right? If you look around in applied math and machine learning, and in the whole field of so-called artificial intelligence, mostly that's great, but there's a very large group that does not question the precision of the functional very much anymore. The quantum chemists, of course, do that a lot. Right?
Yeah.
But then if you look around, then you very quickly enter the very murky field of so-called correlated materials, and all sorts of problems arise there.
Yeah.
So one question is if some of these problems are actually related to this aspect here.
Yeah, no, it's so just to answer that, like, in a two-piece format, I'm running out of time, so I want to, like, maybe finish the last thought, but I'll answer and maybe take like a couple minutes to finish the Kohn-Sham equations. Is that from a mathematical standpoint, the V representability problem is still open. We do not know the function space of the electron densities, which actually come from a true quantum mechanical calculation. Now, still from a practical standpoint, you just use the functional approximation and then go with the electron density for various systems. It is a practical approach. And I think the choice of the exchange correlation functional is very critical. Also, in the many studies which were done, I'll talk about this like in the next lecture tomorrow, like what are all the approximations which go on in Kohn-Sham DFT. And I will bring up like the hybrid formulations and other things. One has to. So the effort to go and figure this thing out is a 50-year-old effort, and still some of those functionals like PBE and other things which have been developed in the field have 100,000 citations. I mean, so they're practically very widely used. If somebody is able to figure that out, I think maybe the next Nobel Prize. But it's an open question. So I'll leave that there. I'll continue more on the exchange correlation approximation problem in tomorrow's lecture. There I will be using slides, so I'll go quicker. So this is what is the Kohn-Sham eigenvalue problem that we end up getting. And so the electron density is computed as summation over I, Fi mod psi I square, where Fi's are, this is the occupancy. So because we are interested in the ground state properties, we are trying to like fill all the orbitals, which are the lowest lying orbitals, with 1, and then what are not occupied will be 0. So it's technically like a step function. But if you use a step function, like, you will end up getting numerical instability. So you kind of smear that out using Fermi-Dirac smearing, or there are other types of smearings that people practically use. So the two challenges over here in solving the Kohn-Sham equations. First, we are solving an eigenvalue problem where we have to compute as many eigenstates as there are number of electrons in the system. Because this is a single particle, each state is occupied by one of the electrons. I mean, doubly occupied, like, if you account for, if both the spin up and spin downs have the same spatial orbital. But essentially, you're roughly computing the number of eigenstates that are proportional to the number of electrons in the system. So if you're doing like a 1,000,000 electron system, you have to compute 1,000,000 eigenvalues for this particular problem. That's the first challenge. And that scales, if you were doing it in a naive way, that will scale as order n cube. And there have been like other methods. I'll talk about this in tomorrow's lecture. There have been other methods like where they've tried to reduce that computational complexity. But in a most generic manner, it is still cubic scaling for any general material system. So that's one thing. And then second thing is this is a nonlinear eigenvalue problem. So which means that we have to assume an input electron density, and then we compute this eigenvalue problem. Then we get an output electron density that comes from this expression. If the input electron density is not the same as the output electron density, then you have a fixed point iteration, right? And again, the convergence of the fixed point iteration, the many numerical approaches that people have developed, but these are primarily have been developed for small to medium scale systems. Once the system size becomes large, that fixed point iteration convergence itself may become a challenge. So you have like, this two aspects over here, one being solution to really large scale eigenvalue problem in conjunction with the solution to the fixed point iteration. And again, this is what makes like doing DFT calculations on an exascale computing challenging, because now depending on the choice of the basis set, this could be a dense matrix, this could be a sparse matrix, but a much larger sparse matrix. You have a very large eigenvalue problem involving many, many eigenstates. And if you want to use an exascale computer to like really go for like larger scale systems, then the fixed point iteration algorithms, I mean, also need to be looked at, because once you're pushing the limits of what is the accessible system size, that can also become a bottleneck. So I'll touch upon all these aspects like in the lecture tomorrow. Thank you.